Hello everybody, welcome back to the Gregorius Maths video. In this video, we're going to be looking at some exterior algebra, differential forms, and then we're briefly going to look into integration on manifolds. So I'm going to define it, prove it's well defined, and then I'll state Stokes' theorem. I'll see if I prove it or not. And then, well, yeah. If I don't prove Stokes' theorem, I'll do a separate video on integration on manifolds where these prerequisites are assumed, and I prove Stokes' theorem and do more detailed video on integration on manifolds, because this is more of an intro to the machinery we need to understand integration on manifolds rather than a proper video about integration on manifolds. So I might just state Stokes' theorem and prove that, define the integration map and show it's well defined. But before I get into this video, unfortunately differential geometry 1.1 will not be enough prerequisites for this video. Although, thankfully, there is a YouTuber who has a playlist about manifolds called Fematica. Fematika. Fematica. And, well, his manifold series is excellent, and it's pretty much all the prerequisites needed for this video. I'm sure you've heard of Fematica if you're watching this, but yeah, his videos are pretty much a list of prerequisites for this video, and they are just in general really great videos, so I recommend that you check him out anyway, his channel out. And okay, so yeah, so I'll put timestamps in the description for the exterior algebra, the differential forms, and the integration on manifolds, so that if you're just here for one of them, you can skip to that part. And also I have a few videos lined up. I've got one on spectral sequences, which I might do. I might do some more stuff about differential geometry. Maybe I'll do some stuff about hyperbolic manifolds, who knows. But yeah, I've got quite a few different possibilities for videos going on. I might do one on spectral sequences, adding to the because why not playlist. So yeah, let's just get into it. So we say that T is a p-tensor over V if it is a multilinear function over V to the p. And this is of course equal to V times V p times. Okay, so it has to be linear each variable, basically. So this is what we mean by a p-tensor. And, well, the vector space of p-tensors over V is denoted G to the P of V star. Alright, so this is the vector space of p-tensors. And, well, a natural question to ask is, can we combine two tensors into one? So given a p-tensor and a v-tensor both over V, can we have a p plus q tensor over V? Or basically, can we just construct a new p-tensor? And we do this very easily with the tensor product. So if T is in the space of V tensors, P tensors over V, and S is similarly a Q tensor over V, then we say that T tensor S is a P plus Q tensor over V, and it's defined as T tensor S is equal to T of V1 up until Vp times S of Vp plus 1, up until Vp plus Q. And there are a couple of obvious properties of this. It's not commutative at all, since s of v1 is probably not going to be s of v1 up until vp is not going to be equal to s of vp plus 1 up until vp plus q in the normal case, and it is associative. T tensor s tensor r does equal T tensor the quantity S tensor R. And that just follows from the associativity of multiplication. Alright. Now let's move on. So there's a special type of tensor, and this is called an alternating p-tensor. So we say that a p-tensor T is alternating if, well, T of V1 up until Vi up until Vj up until Vp is equal to negative T of V1 up until Vj up until Vi up until Vp. So swapping two of the inputs just makes the output negative. And, well, obviously, this is going to be heavily related to the permutation group. Since we're permutating the inputs, we want to consider, well, this in more general terms. So, if we let pi be in the permutation group of p, so this is a group under the operation, with respect to the operation of composition, then this is the group of permutations of p, and it's a group with respect to composition. Then we say that t to the pi equal to t of, so we say that t to the pi, and then you apply it to v1 up until vp, and it's equal to t of the first permutation, v sub the first permutation, up until the pth permutation. And obviously, t to the pi is equal to negative 1 to the pi t. Because what this is basically saying is that if you permutate t, the inputs, an even amount of times, you're going to get your tensor back. And if you permutate an odd amount of times, you're going to get the odd version, the negative version of your tensor back. Okay? And, yeah, so that's that. And now, we can construct alt of t. Right? So, so alt of t is defined as 1 over p factorial times the sum over all pi in the permutation, so all the permutations, of negative 1 to the pi t to the pi. And the first theorem of the day is that this tensor is actually alternating. So and the proof is quite simple, it's just a simple computation. We want to show that alt of t to the sigma is equal to negative 1 to the sigma alt of t. So let's just do that. Alt of t to the sigma is equal to negative 1 to the sigma 1 over p factorial times the sum over all pi in the permutations of negative 1 to the p composed sigma t to the pi composed sigma. And now, letting tau equal pi composed sigma, we get that this is the alt of t to the sigma is equal to negative 1 to the sigma 1 over p factorial times the sum over all tau in the permutations of negative 1 to the tau t to the tau, and this is -1 to the sigma alt of t. And this is -1 to the sigma, and this is -1 to the sigma alt of t. Right? Okay, so let's see what happened here. Tau was pi composed sigma. And then how come this and this are the same? Well, this is because if pi ranges over all the permutations, since a group is closed, since the group is with respect to this operation, the group is closed under this operation. So if pi runs over all of them, tau is also going to run over all of them. Then we get -1 to the sigma alt of t, right? Because this is precisely alt of t. And this actually proves it. Because we proved that alt of t to the sigma is equal to -1 to the sigma alt of t, and that's precisely what we wanted. And, well, now that we're equipped with a decent understanding of this alt here, well then, we have another natural question. Given two alternating tensors, can we make another alternating tensor, just like with the tensor product, except this is with alternating tensors? In fact, we can. So given T, an alternating P tensor, P tensor over V, and S, an alternating Q tensor over V, then we define T wedge S in this subspace. So this forms a subspace of the space of alternating P tensors over V, or V star, by T wedge S is equal to alt of T tensor S. And, well, this is a much more interesting operation than the tensor product. And this is the one we're going to be working with. And actually, turns out that it takes quite a bit of work to prove this, and it's not really the intention of this video, so I'll just state this. Given alternating tensors, alternating P, Q, and R tensors, I'm not going to write that out because it's a bit tedious, and you know what I mean. Essentially, the wedge product is associative, and it's anti-commutative, so T wedge S is equal to -1 to the P Q S wedge R, where of course P and Q are, well, T is a P tensor and Q is an S is a Q tensor. Okay? Yeah, that's enough exterior algebra for understanding integration on manifolds, so we'll move on. Next, you have to look at differential forms. So let's just go straight away. So, a P form is a function omega such that for some smooth manifold X and some point X in X, we have it that omega of X is an alternating P tensor over the tangent space of X at X. Alright, so for every X in the some smooth manifold X, it assigns to it an alternating P tensor on the tangent space of X, over the tangent space of X at X. Okay? Now, a zero form is a real valued function. A zero form, real valued function from x to r. And so for every zero form, we can associate to it alright, a 1 form, d, alright, so let's just call this map phi. So it's phi. We can associate to it a 1 form d phi sub x, which takes you from the tangent space of x at x into r, alright, into, oh my goodness, onto r. Alright, so actually we can do this in general. So for zero forms we can assign it a linear. This is a linear map. So this 1 form is a linear map called the differential. Alright, so this d phi x is a linear map called the differential. And in general, we have the exterior derivative, which takes in a p form and outputs p plus 1 form. So, definition. Oh, good lord. Okay, here we go. Given a p form, omega, of the form the sum of ai dxi, alright, we can construct a p plus 1 form d omega equal to the sum of dai wedge dxi, and this is called the exterior derivative. Okay? So we can associate to every p form a p plus 1 form called the exterior derivative. And again, since it's not really the point of this video, I'll just state the 3 very important properties of this exterior derivative, and also it takes quite a lot of work to prove them. So, essentially, d of omega 1 plus omega 2 is equal to d of omega 1 plus d of omega 2. So it satisfies the sum rule. It satisfies the following Leibniz rule, that d of omega wedge theta is equal to d omega wedge theta plus negative 1 to the k, where k is because they're k forms, of course, omega wedge d theta, and to decompose d of omega is equal to 0. So if you apply the differential twice, you get 0. Alright, now we're ready to define integration. So, given a manifold X, and a p form omega, we define the integral over x of omega to be the sum over I of the integral of p sub I omega, where p sub I is a partition of unity. Okay, and yeah, the theorem I'm going to prove is that this is well defined, so that we get an idea of what we're working with here. Well, for this proof you have to know that the sum over I pi equals 1, and the sum over I of pi omega equals omega, and so the integral over x of omega is well defined. It's well defined. And the proof is as follows. So the integral over x, so assume that there are two partitions of unit 2, pi and p prime j. So then we're going to have the integral over x of pi omega is equal to the sum over j of the integral over x of p prime j pi omega. And the integral over x of p prime j the integral over p prime j omega is equal to the integral over x, the sum over I of the integral over x of p prime j omega. And so now we have that. Combining these results, we get that the sum over I of the integral over x of pi omega is equal to the sum over I of the sum over j, so basically this, of the integral of x of p prime j pi omega. And this is equal to the sum over j of the sum over I of the integral over x, and then we flip these two around, so we're going to get p prime j omega, and this completes the proof because this is equal to the sum over j of the integral over x of p prime j omega. Okay, and now, well, what Stokes' theorem says, and I'll omit the proof for this video. I'll make a separate video with, well, a more detailed account of integration over manifolds and the proof. But what the generalized Stokes' theorem says is that the integral over the boundary of x, so for some given a smooth oriented manifold x, we have it that and a p minus 1 form omega, we have the integral over the boundary of x of omega is equal to the integral over x of d omega. And in the next video, I'll do a more detailed account of just the integration over manifolds. I'll call it differential geometry 1.3. And, well, I'll prove this theorem. See you then. Goodbye.